Today we look at circular motion, and in particular how to do Newton's second law for objects that are moving on a circle, whose path sits on a circle. And what we'll find is that circular motion is really an expression in kinematics. We can describe exactly what the acceleration of an object that moves on a circular path is. And then we'll use that in Newton's second law. In particular, we'll try and choose a coordinate system so we can use the rules that we find in kinematics. First we'll talk about the kinematics of circular motion, both qualitatively, and then we'll derive the expression for centripetal acceleration, as it's called. Then we'll write down the precise statements that we have, what we're going to be able to use in Newton's second law, and then we'll apply it to two examples. So in the first example, I'll sort of show you the basic idea of how to use it, and then we'll do a more complicated one of a car traveling on a banked curve. So first, the kinematics. If you look back in your textbook, you'll see that there was a section on circular motion there, because the topic really is just a kinematics topic. And we've seen it qualitatively, at least, when we talked about the acceleration of an object that moves around a corner. So let's look at that qualitative example first. So if we have a person running around a circular track here, we're looking down on that person. Their velocity vector at each moment will look like this. So the initial velocity would be sort of pointing up the page here, initial velocity. And then a quarter of the track later, they're now moving with, let's say, a constant speed. So the magnitude of their velocity vector is the same, but the velocity vector now points to the right. So it's a changing velocity that we see there because the velocity vector's direction is changing, and therefore they have an acceleration. And we can write that down. So remember, the expression for the average acceleration vector is the change in velocity over the change in time, which just means the final velocity minus the initial velocity divided by the change in time. So if we can find the delta v vector, the change in velocity vector, then that will be exactly the way that the acceleration vector will point. So that's what we'll do. So let's just do a vector addition to find the delta v vector. So if we place our final velocity vector first, and then we add to it the opposite of the initial velocity vector. So that will be this vector. That's the minus initial velocity vector. Then the delta v vector, the resultant of that, will point sort of downward and to the right in this way. Oops. That's our delta v vector. And because of this equation, the equation for the average velocity, the delta v vector points the same way as the acceleration. And so I could say that over this time interval from A to B, there's an acceleration vector that points in this direction. So what do we see? We see that if an object moves on a circular path, the acceleration vector points inward, meaning inward on that circular path. And that's going to be the general statement that we'll have for the entire lecture today. What we want to do is try and make that a little bit more precise, figure out the magnitude of that acceleration, that inward pointing acceleration. But that's the basic idea, and we've already seen it when we did a similar problem like this back in the first couple days of the class. So let's do it quantitatively. And we'll do it considering the runner again, but we'll take a much shorter time interval. So they just run a little bit of the ways around that circle. So let me draw out a couple things on this picture. So first of all, let's choose the radius of this circle. It must be something like that. So I'll call that R. And of course, this radius will be the same to this point here. So that's also R. And over this time interval, they've gone some small angular distance as measured from the center of the circle, and I'll call that delta theta. And then the distance that they travel around this arc, I'll call delta d. So that's the distance around the arc that they've run in that short time interval. There's a little bit of math here which will be useful to us, which is the relationship between those three quantities. And it turns out that the relationship is delta D is equal to r times delta theta, as long as delta theta is measured in radians. So you've seen this equation before, at least in the case of the full circle. If we go around the full circle, then delta theta would be 2 pi, and the right-hand side here would be r times 2 pi, or maybe more familiarly, what is that word? I don't know. It'll be 2 pi r. And what is that? Well, that's the circumference. That's the distance all the way around the circle. So this is just really the equation for the circumference, but choosing a very small angle of the circumference, and it works all the way around. So that will be useful to us. We'll use that in a moment. So just keep that equation there. I'm going to redraw it so that things don't get too ugly looking. So here's our r. And here it is again. And now I want to look at the velocity vectors as the person runs across there. So here's our delta theta. The velocity vector initially, well, it's always tangent to the path. So here it is horizontal. That's our initial velocity vector. And then tangent to the path a moment later will look like this. So that's our v final vector. So let's again calculate the average acceleration. So the average acceleration is delta v over delta t. So I want to find the delta v vector. But what I'm interested now in is the magnitude of the average acceleration. So you just take the magnitude of both sides, and that will be the magnitude of delta v over delta t. And we'll use that in a moment. But let's look at what the delta v vector looks like. So we have coordinate system, and we'll place our v final vector there. So it looks something like, I don't know, this. That's v final. And then we add to it the opposite of the v initial vector, and that looks something like this. So this is minus v initial. And our delta v then is this resultant vector here. And again, you see that that points inward on the path. It means that their acceleration vector will be looking something like this. If I look at this little triangle, I can draw it like this, where each side is just the speed of the runner, because we're assuming that the magnitude of the initial and the final velocities are the same. The opposite side here will be the delta v magnitude, and then the angle, well, if you look at this picture up here, you see that the angle here will be translated exactly as the angle between the two vectors, and that's because the vectors are always perpendicular to this radius, and therefore if the angle goes over by theta degrees in the circle, then the final vector will come down by exactly that same amount relative to the initial vector. So if we just draw this out here, that means that this is delta theta, and that this is delta theta, or in our triangle, we have delta theta here. So we have this small triangle which relates the velocity, the theta, and the delta v, and you can see that this triangle looks very similar to the thing we did over here. So I can write that delta v, which is approximately the arc length of a circle, is approximately v times delta theta. Sorry, that's not delta v vector, it's delta v magnitude. So I'm just applying to this triangle exactly the same rule that we applied over in the other triangle. Okay, now we're ready to calculate the average acceleration. So the average acceleration magnitude is delta v magnitude over delta t, And we just found an expression for delta v magnitude. It's the speed times delta theta. But delta theta, we also have an expression for. So over here, we just wrote down an expression for delta d, but that means delta theta is equal to delta d over r. So I can replace that in my equation. So I have v times delta d over r all over delta t. And what I find is that I get v over r times delta d over delta t. But delta d over delta t, well, that is just the distance traveled along the path divided by the amount of time. It's just the speed. So that itself is also equal to v. So my final result is that the magnitude of the average acceleration is v squared over r. And that will hold up to be exactly the value of the average acceleration as you make the time interval shorter and shorter. So we've just found the value of the acceleration for an object that travels on a circular path with a constant speed, and we'll use that from now on. So what are the precise statements about circular motion? Well, we just proved one of them, which is so-called uniform circular motion. So uniform in this case means that the object is traveling with a constant speed. So when an object travels on a circular path of radius r with constant speed, the acceleration vector is, well, two things. It's a vector. The magnitude is v squared over r, and the direction is called radially inward. So let's sketch it out on this picture. So radially inward means that it points directly at the center of the circle. So if this is the center of the circle here, it's pointing directly there. And another way to talk about that is to define what's called the radial axis. So we'll call it the r-axis. And the r-axis points outward from the center of the circle through the object. And we see that the acceleration vector points in the negative r direction. That's what we mean by radially inward. If this object is traveling in this direction, if its velocity vector goes like that, then we call this perpendicular direction the tangential direction. So this is tangential, and the other axis is radial. So we can specify the acceleration vector's components in terms of that coordinate system. So if we do that, then a vector is going to be equal to ar comma at, where ar is going to be a negative number equal to minus v squared over capital R, the radius, and at, well, it doesn't point in the t direction at all, so it's 0. So this is for uniform circular motion. The acceleration vector points directly inward, which we now call the negative radial direction, and it does not point forward or backwards, which we could call the tangential direction. So that's uniform circular motion. What about general circular motion? So what I mean by that is the object is still traveling on a circular path, but we don't require that it maintains a constant speed. So let's sketch that out here. So maybe here their velocity vector in the initial moment looks like this, and then a slight time later, still tangent to the path, but it's a little bit longer, v2, and then still tangent to the path, but a little bit longer, v3, and then finally tangent to the path, but much longer, so getting faster and faster and faster. Let's call this v4. I don't know what happened to my 3 there. So we have an object that travels on a circular path. I started that as a circle, but now it's speeding up along that path. So you could ask, what is its acceleration at some moment along that path, maybe right here where I drew the v2 vector. So what is its acceleration there? Well, we can expect that it will be traveling with an acceleration that points somehow inward. So if we draw an axis from the center of the circle through the object at that point, we can call that the radial axis. So this is the center of the circle. And we can expect that there should be some component to the acceleration vector, which is radially inward, which has a negative AR value. But because it's speeding up in the direction of its motion, because the speed is getting larger, we should also expect that there is a positive tangential component now. So if we look at this tangential direction, there should be an AT value, which is positive. And that just means that it's speeding up along the path. So what does that mean? It means that the acceleration vector in general would point inward, but sort of directed forwards as well. So it looks something like this for an acceleration vector. So a forward pointing but inward pointing acceleration vector. Well, that seems more complicated. It seems like we've sort of lost any precision that we're able to use, but there's a wonderful thing that happens, which is that the value of AR remains exactly the same. It remains to be minus v squared over r. So for uniform circular motion, we found that the inward pointing acceleration, which we sometimes call the centripetal acceleration, is v squared over r. Well, even if the object is speeding up or slowing down, the radial component will remain the same. It will still have a v squared over r if you find the component of that vector there. And we might use that in some problems. So these are the statements that we have to use about circular motion, and now we'll apply them to Newton's second law. So the point of what we found so far is that we know exactly what the AR value is. We know what the radial component of the acceleration is for an object moving in a circle. So if we're given a problem where an object moves on a circular path, then what we want to do is choose the radial axis as one of our coordinate directions. And if we do that, then because Newton's second law says F net is equal to ma, then the a will become an AR in the radial component equation, and we can just plug in the value for AR that we know it should have. So that's really the only new thing that we need to learn today in using Newton's second law, is making that choice, meaning finding the circle, finding the center of the circle, and choosing an axis that points outward through the object. So let's see how that applies in an example here. So we have a person who's swinging a bucket, and that bucket is making a vertical circle around the person here. And the question is, what speed does it have to have when it goes through the top of that circle so that the ball that's sitting in the bucket doesn't fall out? So you may have done this before. If you swing something around in a circle, like a bucket, then you find that the stuff doesn't fall out at the top. And that's related to this circular acceleration, and we'll try to see how that works. So here's a picture of the bucket at the top of the circle. So maybe I should draw the path a little bit just so that we see it's moving on a circular path. Its velocity vector is tangent to that path. It's just horizontal at that moment, so I could draw the velocity vector there. And now we're going to apply Newton's second law. So we want to draw a free body diagram. So what are the forces on the ball? Well, it has mass, so we draw a force of gravity vector. And we see that the ball is also in contact with the bucket. So there's a surface of contact, which actually sits above the ball because the bucket's floor is just above the ball there. And the normal force points perpendicular to that surface of contact. So whenever you're in contact with something, you have a normal force. And in this case, that normal force is pointing down on the ball. So we have two forces pointing down on the ball. Our free body diagram is not finished because we also should include the acceleration vector. Well, we know that it's circular motion. We know that it's going around this vertical circle, and therefore the acceleration is pointing inward. So I can draw an acceleration vector that also points down. So you might say, well, how do I know it's not speeding up or slowing down at this moment? Well, if the picture is as I showed it, then there are only two forces acting, and both of them are vertical. So it's impossible for the acceleration vector to be pointing downward. Maybe if the ball was sitting over here on the edge, then there could be a normal force pushing it forwards, and then we would get a different acceleration vector. But in this case, we know that it points directly downward. So there's our free body diagram, and now we can just do Newton's second law. So we have F net vector is equal to ma, meaning sum of the forces is equal to mass times acceleration. We have the sum of the forces, meaning Fg plus Fn, that's equal to ma. And now at this point, we choose a coordinate system. So this is the one special thing that we learned today, which is that we want to choose a coordinate system that gives us the AR. So I find the center of the circle that it's sitting on, and I draw an axis that points outward from the center of that circle, and I call it the radial axis. Now I could draw another axis perpendicular. Well, if this is the velocity, then we know the name of this one. It's called the tangential axis. That one doesn't matter because none of the vectors point in that direction. So we'll just use the radial axis, and we can start that now. So we have the radial equation is FGR plus FNR is equal to MAR. That's our radial equation. And let's find those components. So FGR, well, FG points downward, and with respect to this radial axis, that's in the negative R direction. So this becomes minus FG. Fn also points downward, so it's going to have a negative R component. So that's minus Fn. And A also points downward, and so it will also have a negative R component, but we know exactly what that is. So we found on the previous page that AR is equal to minus V squared over R all the time. So I can write here minus V squared over R to replace for AR. So this was the main point. The main point was choosing the R axis and then substituting AR with minus V squared over the radius of the circle. Now we can try and solve our problem. So this equation becomes, if I multiply through by minus 1, then I get mg plus Fn is equal to mv squared over R. That's my boxed equation. And let's try and figure out what we want from that. So what's the question that was asked? It says, what's the minimum speed that the bucket and ball have to have such that the ball doesn't fall out? Well, how does the speed change here? Let's rewrite this equation down below. So we have mg plus Fn is equal to mv squared over R. So if the speed goes down, then what must be true in this equation? Well, that's the right-hand side going down. The mass and the radius must remain the same. If the right-hand side goes down, then the left-hand side must also go down. But mg, well, that cannot change. That's the mass of the object times g. Those are both constants. So the only thing that can change is Fn. So we see that if v goes down, then the normal force magnitude also goes down. It must be. It's the only way. So what does it mean, minimum velocity? Well, it's the value that the velocity hits when Fn goes to 0. So we can say v min when Fn is equal to 0, because that's the least that the normal force can be, 0. And of course, if Fn goes to 0, then that means that the ball has broken contact. The ball is no longer in contact with the bucket, which is exactly what we were talking about up here, the ball falling out. So it all fits together. A minimum velocity is the moment at which the normal force goes to 0, and that means the ball has broken contact and fallen out. So we take that as our case. So we say, choose Fn going to 0 so that v goes to the minimum value. And then we can solve for that. So we get mg plus 0 is equal to m times v min squared over r. And that means mg is equal to m v min squared over r. I can divide both sides by m, and I can multiply both sides by r, and I get v min is equal to the square root of gr. So what is that? Well, interestingly, it doesn't depend on the ball. So it doesn't matter what the mass of the ball is. the minimum speed is going to be the same regardless of the mass of the ball. So let's just type it into the calculator. So we have square root of 9.8. Oh, we don't have a radius. Oh, I plugged in a radius up there. It's 1.5 meters. So 9.8 times 1.5, the square root of that is 3.8. So the minimum velocity is 3.8 meters per second, the minimum speed. If you go any slower than that, then that means Fn went to 0 and the ball falls out. And if you go faster, well, a larger v means that Fn is larger, and so the ball will be very well stuck to the top of the bucket there with some large Fn. Okay, all of that is Newton's second law stuff. The important part, as I said before, is choosing a particular axis in your coordinate system choice, and then applying that choice by writing AR in this particular way that we found from kinematics. And that's it. The rest of it is just the application of Newton's second law. So let's do one more example. So we have a car traveling around a curve, and we say that the radius of curvature of that curve is 160 meters. And we're told the car is driving 55 miles an hour, which turns out is 25 meters per second. So what should the banking angle of the curve be so that friction is not necessary to keep the car on the road? Well, let's look at it. So the picture here is that we have a road that's angled with respect to the horizontal, and the car is driving on that banked curve. So it's going to look something like this. So this is the front of the car, let's say. This is the grille, and then here you are driving the car. There you are. So the car is at an angle, but where is it driving? So it's going to be driving in a circle. We're told that this is a circle. And so what does it look like? If we look at the entire circle, like maybe it's a racetrack, and maybe you've seen this for like NASCAR. Here's the car coming at us. There you are. And then the car goes around the circle, out of the page, and then turns and goes away from us on the other side. So these are the tail lights and the license plate. Do they have license plate on NASCAR? I don't think so. And there you are driving away from us. So that's the circle. The circle comes out of the page, and then the car goes back into the page, and then comes out of the page, etc. So where's the center of the circle? Well, the center of the circle is like above the ground somewhere, at the center of this loop, and then it just goes around and around like that. So the circle, it's hard for me to draw it, but the circle is something like an elevated circle like that. So that's the picture, which means that on the first picture that I drew, there should be a center of the circle somewhere here. So this is the center of the circle. And then there's a radius, which could be large, which goes from there to there. And the radius, we're told, is 160 meters. Okay? So we want to do Newton's second law here, so let's do a free body diagram for the car. So here's our dot for the free body diagram. And what are the forces acting? Well, we have gravity, because the car has mass, so Fg. And then the car is in contact with the road, so there's a surface of contact there. So there will be a normal force acting on the car, like this. Now what else? Well, the question that we're asked, or at least the first question that we're asked, is what should the banking angle be so that friction is not necessary to keep the car on the road? So normally with a car on a road, there is some friction between the tires and the road. But what this is saying is, what if there was a snowstorm and there's no friction at all? How steep does this have to be so the car doesn't slide off the road? So in this case, in part A, we're going to ignore friction completely. And these are the only forces that we have. They're the only ones that allow the car to go in that circle. So our free body diagram is not quite done. We need to draw the acceleration vector, and we know that the car is moving on a circle, so the acceleration is going to be going inward on the circle. It's moving with constant speed, so it's directly inward, and therefore on this picture the acceleration vector should look like this. It's a directly inward acceleration vector. And that's it. That's our free body diagram. So let's do Newton's second law. We have the sum of the forces is equal to the mass times the acceleration. And in this free body diagram, our forces are normal and gravity. So that sum is equal to the mass times the acceleration. And now we must choose a coordinate system. Well, you know how this goes now. We don't want to choose just any coordinate system. Even though you're allowed to, the one that will make it easy to solve is by choosing a coordinate system that points radially. So I choose one axis that points like that, and then I could just choose the other axis, so Fn points and Fg point in other directions as well, so I'll need a second axis, and I'm just going to call that the y direction. So we have the r direction and the y direction. That's not the tangential in this case. I guess tangential would be pointing directly out of the page at us. So that's not a useful one to choose right now. So let's write down the component equations. So in the r direction, we have FNR plus FGR is equal to MAR. And then we find them. So FNR, well, let's draw that out for ourselves to try and make it clear. So draw a copy of the coordinate system, r and y, and then I'm going to draw, oh, I guess it's pointing upward here. So Fn points like this, and I'm trying to find the r component, so that's going to be this tick mark here, FNR. So what is that? Well, we see that it points on, it's a point on the negative r axis, so we're going to have a negative number there, and it's going to be related to the angle. So let's draw the banking angle. So the banking angle is going to be this theta, which we don't yet know what it is. And how does that relate to the angles next to the normal force? Well, you can see here that if the banking angle was 0, then the road would be flat, and the normal force would point directly upwards. But as you angle this upwards, as you push the road up at an angle, then the normal force goes from vertical to slightly leftwards. So that means that this angle right here is exactly theta. And then from some geometry, that means that this angle is also theta. So we can now figure out what the component of Fn is. We could draw, for example, this triangle. So this triangle has Fn magnitude on the hypotenuse, and here's our theta, and x is what we're looking for. So we see sine theta is equal to x over Fn, or x is equal to Fn sine of theta. And FNR, the component, is a negative number, which is minus that. So we write minus Fn sine theta for FNR. What is FGR? Well, FG just points along the y-axis, so it has a 0 r component, so I write plus 0 for that. And then AR, well, A is a vector that points inward. It points in the negative r direction. In fact, that's the whole reason we chose the r direction as one of our components. So let's just draw it out quickly. Another copy of the coordinate system. We have the A vector pointing in this direction, which means that A sub r is that negative number, and we know exactly what that negative number is. From kinematics, it's minus v squared over capital R. So that was our main point. We've now done the circular motion part of it. So that equation, before we put a box on it, let's make it look a little nicer. So it's Fn sine theta is equal to mv squared over r. There it is. Now, can we solve anything yet? Well, the question is, what should the angle be? So that's unknown, such that at 55 miles per hour, the car doesn't slip, meaning such that this free body diagram is okay. Well, we don't know what the normal force is, so we can't do anything yet with this equation. We have two unknowns, normal and theta. So we need another equation, and that will be the y component equation. So that is fny plus fgy is equal to may. Fny, well, that would be this tick mark right here. We see that that's a positive number. And we see that that's going to be related, because we already did sine theta for the x direction, it's going to be related to cosine theta for the y direction. So you should check it, but I think it's going to be Fn cosine theta. Fgy, well, that points just down the negative y-axis, so it's just going to be equal to minus Fg. And Ay, well, we saw it already. We drew this picture here, and we see that it only points along the r-axis. I don't know why my y looks so weird there, but it has a 0 y component. So may just becomes m times 0, which is 0. So this equation becomes Fn cosine theta is equal to mg, using our equation for Fg. There we go. Now I think we're ready to solve. So we can solve one equation for Fn, plug it into the other equation, and then we'll have an equation only for theta. So we'll do that. Let me do it below here. So this becomes Fn is equal to mg over cosine theta. And then I can plug that in to this equation. So I get mg over cosine theta multiplying sine theta is equal to mv squared over r. Well, it looks like the mass cancels out. I can divide both sides by m. So in this banked car example, the result that we get doesn't depend at all on the mass of the car. So it doesn't matter if you have a Ford F-150 or a Mini, the result will be the same, the angle that's needed to keep the car on the road. So what do we get? Well, I could divide both sides by g, and then sine over cosine becomes tangent. So I get tangent theta is equal to v squared over gr. And we're looking for that theta. So theta, taking the inverse tangent of both sides, is going to be the inverse tangent of v squared over gr. So what is that? We need to plug into the calculator. So we get inverse tangent of, our v was 25 meters per second. The square of that divided by 9.8 divided by our radius of curvature, which was 160 meters. And we get 21.7 degrees, so about 22 degrees. So if you want a car to be able to drive around a 160 meter radius of curvature circle, then you need to have an angle of 22 degrees so that it doesn't slide off. In all conditions, whether there's ice on the road or whatever, it needs to be like that. Now the second question that was asked is, okay, now that we have an angle set at 22 degrees, what if there is some friction on the road? So if we have a coefficient of static friction, which is 0.3, then 55 miles per hour is not the fastest you can go. You should be able to go faster than that. So what's the maximum speed you can go on that banked curve as long as there is friction? So let's check that out. So we're going to get a new free body diagram, so we need to redraw this whole thing. So let's draw our banked curve again. And we'll draw the car again. So we have the car, and it's coming at us. And here you are, driving the car, And the free body diagram now, well, it's mostly the same. The car still has mass, Fg, and there is still a surface of contact between the car and the road. So there's going to be a normal force perpendicular to that surface of contact. Here's our Fn. But now we're including a coefficient of static friction. So there's like a mu s, which is equal to 0.3 here. And we're also saying we know that the angle is now exactly 22 degrees. So if there's a coefficient of static friction, what does that do? Well, if the car starts moving more quickly than 55 miles per hour, then it's going to want to continue off in a straight line, and it's not going to continue on this circle, meaning it's going to break away from the circle. And breaking away from the circle in this picture means sliding up the ramp, sliding away. So in this picture, the force of static friction, if that's going to be holding it on, then it must be a force that points down the ramp. So this is the force of static friction that prevents the car from sliding off the road in this direction here. So that will be our new free body diagram. So what does that mean? Well, if there's going to be that set of forces, there must be an acceleration. And of course, it's going to be the same acceleration that we saw before, where the center of the circle is over here. Center of the circle. And the acceleration is pointing towards the center of that circle. So it's exactly a horizontal acceleration. And I guess that's our free body diagram now. So we can do Newton's second law. So we have F net is equal to ma. And now we have a new sum of forces, which is the normal force plus the force of gravity plus the force of static friction is equal to ma. And now we need a coordinate system, but we know what we want to choose. We want to choose a radial coordinate system, meaning an axis that comes out from the center of the circle and goes through the object. And then we could just choose a perpendicular coordinate system to that. Again, we'll choose the y-axis. And that way we'll be able to get an a sub r, which is what we need. So let's look at that radial coordinate system first. So we have FNR plus FGR plus F friction static R is equal to MAR. And we've calculated some of these already. We know that FNR, because of the fact that the angle of the ramp is the same as the angle up here, we know that that FNR is going to be a negative number, which is equal to minus Fn sine of theta. FGR is going to be equal to 0 because it just points along the y-axis. And F friction static, well, we should write that one out. So F friction static, it points down in this quadrant here. So there it is. And what is its angle? Which one of those is theta? Well, it's the same story as with the normal force. If this bank was brought down to 0 angle, meaning a flat road, then that force of static friction would be horizontal. So as you bring the angle up, the force of friction is going down there. So that means that this angle right here is theta. And if we just draw a little triangle, we have force of static friction on the hypotenuse. We have theta here, and then we're looking for this side right here. So that's going to be cosine theta. Cosine theta is equal to x over force of friction static. And we can write, well, this component that we're looking for is a negative number. It's on the negative r-axis. And therefore, we can write it as minus F friction static cosine of theta. So those are our force components. And now we need the acceleration. Well, it's the same as before. You see that it's pointing backwards. It's in the negative r direction. So it's just going to be equal to minus v squared over r, because we know its value from our circular motion kinematics. So let's just clean up that equation before we go on. Well, each has a negative sign, so I can multiply through by -1, and I get Fn sine of theta plus F friction static cosine of theta is equal to mv squared over r. And there's my boxed equation. Okay. We're definitely not finished because we're looking for v, and we have a number of unknowns, both normal and static friction. So we're going to need another equation, and that will be our y equation. So let's write it out. Fny plus Fgy plus, if we look back up here to see what our forces are, F friction static y is equal to MAY. I'm looking at my vector equation to find my components. And then we go through and find them. Well, we found last time the y component of the normal force is going to be a positive number, and it's related to cosine theta. So that's going to be Fn cosine of theta. Fgy, that points in the negative y direction. So it's just minus Fg. And the force of static friction y, well, if we look at this picture here, it's going to be this tick mark, this number, and that will be related to sine of theta, because the other one was cosine, and you see it's negative, so it's going to be minus F friction static sine of theta. And then the acceleration points horizontally, so it has a 0 y component. So this just becomes 0 right here. So our full equation, let's write it out. It's going to be Fn cosine of theta minus F friction static sine of theta is equal to mg. Just plug in the equation for the force of gravity there. So there it is. So if there's an answer to this question, we should be able to find it from our boxed equations. We need to do a little bit of thought here, though. So what do we mean by the maximum speed? Well, it's the maximum speed at which you can go before the force of static friction breaks. Remember, the force of static friction can be provided up to a breaking point, at which point we know its equation. We know that it's equal to mu s Fn. But it's only at that point that we can use that equation. So let's just write that out for ourselves. So we seek V max where the force of static friction is equal in magnitude to the maximum force of static friction. And that thing we have an equation for. That thing is mu s Fn. So we're looking for the breaking point. We're looking for the maximum value of V, and at that maximum value of V, we can plug in for F friction mu s Fn. So let's do that. We're looking for this equation, so maybe we should adjust this equation first. So let's solve for Fn, and then we'll plug that expression for Fn up here. So let's see. So we have, well, first we got to use this. So we have Fn cosine theta minus, and this comes from this equation here, and I plug in mu s Fn for F friction static times sine of theta is equal to mg, which means that if I pull out, factor out Fn, I get Fn times cosine minus mu s sine is equal to mg, or Fn is equal to mg over cosine theta minus mu s sine of theta. Okay, so now I have an expression for Fn, and now I want to use this equation, and I want to plug into it. So let's just rewrite it down here. So that's our first equation. I can again plug in my expression for the force of static friction, so that becomes mu s Fn cosine theta here And then when I do that, I must say that this is now the maximum speed. So I'm choosing the special case where force of static friction is breaking, and therefore it's equal to mu s Fn, and at that moment, our v is called the maximum speed. So I plug that in as well. And that means that I have Fn times sine of theta plus mu s cosine theta is equal to m v max squared. And now I want to plug in my expression up here for Fn. So I get mg over cosine theta minus mu s sine of theta times sine of theta plus mu s cosine theta is equal to m v max squared over r. What are we looking for? Well, we were given mu s, we were given the theta. Remember, we built the banked curve at 22 degrees, and we're looking for now the maximum speed that you can drive on that banked curve, given that there is some friction. Well, one interesting thing happens is that the mass, again, cancels out. You can divide both sides by m. M is just multiplying both sides here. So it turns out that our result, again, does not depend on the weight of the car. The mass of the car does not matter in terms of keeping it on the road. So why is that? Well, the mass of the car certainly affects the normal force, right? Because the mass of the car will determine, in part, the normal force. And so that normal force will be larger because of a larger mass of the car, and therefore the frictional force will be larger. So why doesn't that keep the car on the road better? Well, in order for the car to go around the corner, you need to have a larger acceleration as well, and that depends on the car as well. So, sorry, not a larger acceleration, but a larger net force inward, which is determined by mv squared over r here. So the mass appears in both places and it cancels out. So your big F-150 doesn't help you any more than the little Honda Civic. So what is the answer? Well, let's do the algebra. Looking for V max, well, it looks like you just need to multiply both sides by R and take a square root. So we have V max is equal to the square root of r times this numerator, g times r times the numerator, sine theta plus mu s cosine theta, divided by the denominator, which is cosine theta minus mu s sine theta. So let's find out what that is. Moment of truth. We'll see if all this work got us anywhere. Hope that that's more than 55 miles per hour. So let's take it. Square root of 9.8 times the radius of curvature is 160 meters times parentheses sine of our angle was 22 degrees plus mu s, which is 0.3, times cosine of our angle, 22 degrees. Okay, and then all of that divided by cosine of our angle minus mu s, 0.3, times sine of our angle, sine of 22, and then the square root of the whole thing. And we get approximately 35, but not miles per hour, 35 meters per second, which is greater than the speed we built the curve for, 25 meters per second, which was 55 miles per hour. So let's figure out what that is in miles per hour. So how do we do that? So 35 meters per second is equal to 35 meters per second times, and now I want to convert to miles per hour. So the factors that I know are, well, there's 1,000 meters in 1 kilometer. And then anybody who's ever run a road race knows that a 10K is equal to 6.2 miles. And then I need to convert the seconds, so we have 60 seconds in 1 minute and 60 minutes in 1 hour. And when I multiply all that through, I should have miles per hour left over. So let's figure out what that, so what I'm saying is meters cancel, kilometers cancel, seconds cancel, minutes cancel, and we're left with miles per hour. So the answer is, let's see, it's 35 times 1 over 1,000 times 6.2 over 10 times 60 times 60. We get 78 miles per hour. So that's how fast you can go before you slide off of the bank that we created with a 22-degree angle. And what's keeping you on beyond 55 miles per hour is the force of static friction. So that's all for the examples, and I hope that you recognize the key point, which is we choose a particular axis in our coordinate system, the radial axis, pointing outward from the center of the circle. And from there, we find that we get an AR, which we know its value to be minus v squared over r. And the rest of it is just our familiar Newton's second law. I'll see you next time.